which to advance?
Forward, it's the bottom one, and the laser pointer. Well, you can try.
Oh, yeah.
But it's the bottom.
Okay, thank you. Well, I'm here to talk to you about the Center for Backyard Astrophysics. Quite a few of you probably know what that is. If you don't know what it is, it's pretty much what you see there. This is a community of telescopes scattered around the world, maybe about 3/4 amateur, about 1/4 professional, and liberally interpreted, these are the locations of the various telescopes. I say liberally interpreted because people drop in and out of this organization. It's not what most people consider a particularly glamorous activity to sit on one star all night long. And then the next night to do it again, and the next night to do it again. 5 years later, still to be doing it. And we do some of that because the purpose is to get long-term light curves which basically can define the periodic content of variable stars without much worry about clouds and about sunlight. Basically, we want the stars never to set on the CBA. And so there it is. It's, for obvious reasons, we're fairly strong in the United States. We're fairly strong in Europe, although Europe being at high latitude, we don't do very well south of the equator, really, for Europe. We have an extremely active observer in South Africa, which is of extraordinary help and allows us to do pretty well in the southern hemisphere. We've completely obliterated New Zealand there. Small tip of the South Island, which is not very good for astronomy. We don't have anybody there, just a bunch of sheep, maybe. And pretty good in Australia, too, including some very, very talented observers. So that's the map of the CBA. And the great majority of the stars that we observe are cataclysmic variables. And just to remind you, that's what they look like up close. They're very short period binary stars, the two stars going around each other, typically every few hours. The shortest one's going around about every 15 minutes. Those are helium stars. Of the hydrogen stars, they vary from about 1 hour to about 10 hours. And this is a time scale, especially the longer time scale. It's very awkward to define from an observing strategy which is based on one location. Basically, the nights are only about 7 hours long or so, and you come from one site, and so you have to wait 17 hours to get the next night, assuming it is clear. And you're often not quite sure how many cycles elapsed during those 17 hours. So this is the problem with aliasing, and it can really never be overcome by single-site telescopes, unless you're up there at declination plus 70 or something, and you're observing in December or something, in which case you can overcome it, but you might not want to be observing that long. So that's the structure of a CV. Too many gadgets here. I'm going to talk about the various kinds of types of CVs that we observe. Right from the beginning, we started observing this class of star called the DQ Hercules stars, or sometimes called the intermediate polars. There's the literary version of a DQ Hercules star up there. There's the light curve that we see typically. These are about 7-hour light curves of a particular star, 6 or 7 hours, and it has a rotational period of 21 minutes. And there's the modulation you can see. It's a fully regular modulation. We've been tracking it since actually 1982, and so we're in our 28th year of tracking it. And the point of doing that is these are accreting white dwarfs. And in this case, accreting magnetic white dwarfs. As material accretes onto the white dwarf, in particular accretes onto the magnetosphere of the white dwarf, spins up the white dwarf. White dwarf has a fairly high moment of inertia compared to a neutron star, for example, and therefore it takes a few years of tracking it just to see the period change a little bit. Typically spin up, spin faster because it's under the action of these accretion torques. And so we observe over long periods of time. We measure the accretion torques, and this is a powerful constraint on the strength of the magnetic field. which is otherwise quite difficult to measure. And so there's an HST image of one of these stars here, where you have the magnetic white dwarf here with a little beam sweeping around, illuminating the disk, to some extent illuminating the secondary star over here with a little hot spot where the stream impacts the disk over there. And here's a sim picture of the shock right above the pole of the white dwarf. Near the white dwarf, the magnetic pressure is very high, dominates the kinetic pressure of accreting matter in the disk. And so everything sort of streams radially down to the surface of the white dwarf. And it's a very, very strong shock because the binding energy, the kinetic energy of stuff falling from more or less infinity, from let's say 3 or 4 white dwarf radii down to the surface, is about 100 kilovolts per proton. So drop a proton radially onto one of these white dwarfs and you get out a 100 kilovolt X-ray. So these things are quite potent X-ray sources. In fact, they're actually, most people don't realize this, most people who work in this field even don't realize this, they're actually harder X-ray sources than the neutron stars, surprisingly. And the reason is that neutron stars that are accreting are typically accreting through the disk, where all the various shock processes are very oblique because nothing is accreting radially, it's just going down, down, down. So the actual irradiating area is actually fairly large. It's comparable or greater than a white dwarf. Here the radiating area is very small. This is typically only a few miles across, whereas the white dwarf is about 1 Earth diameter or so across. So that's one class of star, the DQ Hercules stars. Another class of star that you sort of read about a lot on the various bulletin boards and gets condemned a lot by John Greaves. Did I hear a mention of John Greaves earlier? Anyway, I never met the guy, but I really appreciate his posts. They're very colorful. And he hates superhumps, apparently. Well, we like superhumps. What are superhumps? There are these large amplitude waves in many dwarf nova outbursts that appear typically at or near the maximum of the dwarf nova outburst. They basically are large amplitude waves at a period slightly greater than the orbital period. First one showed up in 1972. People scratched their heads for about 14 years to figure out what kind of a phenomenon is driven by the orbital clock, this very basic underlying clock that underlies all of these close binaries, and yet doesn't really obey it. In fact, not only does it not really obey it, but a typical guy that's about 3% greater than the orbital period, it'll vary from about 4% to about 2%, a little teenage rebellion, just doesn't really do what you wanted it to do. And it wasn't finally solved, actually, until, I think it was 1988. I remember a conference in Seattle when a British graduate student got up and delivered the solution. Nobody had heard of the guy. And he actually disappeared from astronomy shortly thereafter. I don't know what the moral of that is. But we've all been wondering about this thing for a long time, and he explained it as, this is my fancy portable accretion disk. I hope it survives this trip, despite the indignities inflicted on it by Delta Airlines. They really shouldn't have done, since I've paid them for the baggage. But so this is a typical accretion disk. It has the thermal structure of an accretion disk: cool at the outside, hot in the inside. Of course, it's lying in the plane of the orbit, which is why it's in a disk. And pointed out that for certain mass ratios, a spiral structure develops in the disk. And the spiral structure, when tugged on by the secondary, where's my secondary star? I couldn't get a red star, but picture, of course, there are no green stars, so just picture it as an infrared star. It's a little closer to what it is. And this is about to scale. This is about to scale. It turns out, according to this guy, Vincent Mantle, who promptly disappeared from astronomy and returned for his labors, it tugs on the disk, and it produces, in principle, it doesn't always do this, but produces in principle two types of precession. It produces a wobble, analogous to the well-known wobble in the Earth's equator, of course, which produces the 26,000-year precession cycles. It's a slow wobble, quite a bit slower than the orbital period. And it also produces an apsidal. The shape of the disk also pulses in and out, so it produces an ellipticity that then propagates around with a relatively slow period. Every time this thing that's going around with a period of about 2 hours encounters the long axis, it riles up the outer part of the disk, causes a lot of extra light. That indeed is, it's been checked many times, that indeed is the mechanism. In a few slides from now, we'll see how we've interpreted this, or just followed our nose, really, to conclude that this is a way to measure the mass of the secondary. The speed of the wobble. If you can measure the speed of the wobble accurately, you can measure the mass of the secondary. By the way, you can do this in the Earth-Moon system, too, because the Moon's orbit has both of these motions in it. The Moon's orbit wobbles around with an amplitude of 5 degrees. And let's see, the planar wobble proceeds with 18.61 years, which is strongly related to the eclipse cycle, as some of you realize, I'm sure. I'm sure there's some eclipse chasers here. And in addition to that, the ellipticity of the Moon's orbit varies like that. That's why the Moon's orbit has been such a headache for dynamicists for such a long time. And that goes with a period of 8.85 years. So actually, the Earth-Moon-Sun system contains all of these elements in them, analogous to the cataclysmic variable system of basically dominant mass in the white dwarf, perturber mass in the secondary, and sort of victim particles in the disk. So where the Moon is the victim in the solar system case. Okay, so that's why I'm so psyched about the super humps, and we've been stressing it for a pretty long period of time. Okay, and this is just a little, I've been studying these super humps, and we have to measure the orbital frequency. That's pretty easy. Lots of us can do that. And then there's a precession frequency for the line of apsides. The eccentricity precesses around. The nodes precess around. That's the thing analogous to the 26,000 years, or the 18.61 years in the case of the Moon. And we have these super humps. The super humps actually occur at the sideband frequencies. Sorry, it's a little complicated. Not at the precession frequencies, because the two clocks beat together with the sideband frequencies. Ham radio people will know exactly what it is. Probably most of you know what it is. And so you get these various kinds of signals. It turns out you get these various mixing of harmonics as well. Won't go into that. Complicated there. We find a few things other than CVs. You look up in the telescope. With a telescope, you find weird things swimming across your field. This is a very interesting one that happened on Halloween, 2006. Remember, about noontime on Halloween, or a little bit later, it's about 4 p.m. on Halloween, I see this IAU circular appearing from Dan Green or Brian Marsden or somebody, and it reports that a 11th magnitude star has become a 7th magnitude star. This one really caught my eye. I had never known any 11th magnitude stars that just became 7th magnitude stars. And at first I thought, well, it is Halloween. And not only was it Halloween, but it was approximately local midnight in Transylvania. So I thought, this has got some earmarks of a prank. But on the other hand, I know Brian Marsden and Dan Green. I'm sure some of you do. They don't like pranks.
I've got a prank.
They've got...
IE circular from Brian.
You have? Well, okay. I'm going to find out more about this one. Okay, so he still doesn't like pranks, but he apparently likes to perpetrate some. Okay. And anyway, so within the next day or so, fortunately, Bob Koff saw the same thing I did. had pretty much the same reaction, and then that night in Colorado got this data here, which proved to be absolutely essential. And within about a day and a half, there's other reports coming in. There are no X-rays from this thing. The spectroscopy is absolutely normal. The spectrum hasn't changed. It's not some kind of a BE star that threw off a shell or something like that, which might have been a possibility. And so it started to look like a gravitational lens. And I didn't really know that much about gravitational lenses. So but it didn't stop me from speculating, and I fired off some kind of a circular or telegram or something like that. And then a couple days later wrote to some Andy Gould and some experts on gravitational lenses. They said, no, it can't be. Because this star, this 11th magnitude star, it's a pretty nearby star. It's a star only about 1 kiloparsec away. And it's about 1 kiloparsec away. And the likelihood that an intervening star comes within 1 or 2 micro-arc seconds of a nearby star is essentially vanishingly small. And he explained that to me, and I thought, yeah, but what kind of a variable star is it? I thought I knew all the kinds of variable stars there are. Maybe there's another kind of variable star I've never heard of. That's a possibility. So anyway, I wasn't too persuaded about it, and there were some other gravitational lens experts that thought, yeah, that's a possibility. It's at least formally a possibility. Continue to follow it as it declined down here, and then, by a stroke of good fortune, let's see, strangely enough, my golf buddy knew that Grzegorz Pojmanski had just started up the ASAS program in Hawaii. This is in Cassiopeia, this star. So I thought, oh, ASAS is a logical place to check for pre-discovery images. And, but Chile can't reach Hawaii, Cassiopeia. But he happened to know that Pojmanski had just set up this thing. And so I wrote to Pojmanski, have you got any images then? Turns out he did. And he had these pre-discovery images that you see here, including one right at the maximum. To be a gravitational lens, so-called a micro lens, as we call it, you have to be absolutely symmetrical. Unless the lensing star has planets. We were hoping for planets, of course. But as you can see, it really is absolutely symmetrical. There's a fit to a gravitational lens there. And then Andy told me some more about the history of gravitational lenses that really fascinated me. Bohdan Paczynski wrote a paper in 1986 calling this phenomenon to astronomers' attention. But Einstein actually discovered this effect in 1921, shortly after he discovered general relativity. And he showed it to a few people in Germany, but he said it can't be of any importance because the probability for a star to pass in front of another star is just so small. And he showed it to a Hungarian amateur astronomer, among other people there. And this guy got really excited about it. He said, oh, that's really interesting. We ought to publish that, or you ought to publish that. And Einstein said, sure. The guy went away. Every year or so, the guy would keep writing to Einstein, when are you going to publish that thing? It's really important. And he said, I don't know. Didn't answer the mail. Then he, of course, he's a refugee, comes to the United States, buys a house in Princeton, figures he's done with that guy. No more nuisance there. One day, that guy appears on his porch. He says, what about your paper? I'm waiting for this thing. Einstein rolls his eyes. Well, I didn't see him. I wasn't there. But I would imagine he rolled his eyes. And he said, oh, all right, I'll publish something on that thing. And so he published his paper in Science in 1936. No one noticed it. But because Einstein, of course, by that time was a mega celebrity, superhero, I'm sure it wasn't refereed significantly. And the correspondence that Einstein sent to the editor, saying, oh, here's this little thing. It's mathematically correct, but it's really of no importance. But there's this guy that's been bugging me. His last words in the letter, this will make the poor guy happy. So he published it. Still nobody noticed it. It was in 1936. And, well, by 1986, Paczynski noticed it. And now, of course, it's a big industry, of course. Especially for finding planets. Had there been a little wrinkle here, I might be talking about a planet. Okay. I'm going to talk about stellar evolution for most of the rest of the time here. And I'm not going to talk very much about single star evolution because most of you kind of know this story. Follow it from the lower left to the a collapsing gas cloud, depending on its mass. If the mass is under 0.08 solar masses, the object tries the planet works, goes over here. If it's more than 0.08 solar masses, it gets a room in the main sequence boarding house where they allocate rooms by the millions and billions of years. Hangs in there for a while. Depending on how much mass is left over after it's ejected mass in a wind and so forth, it might go immediately to a white dwarf, or it might swell up, become a red giant or supergiant, where they administer leases by the millions of years only. And then, depending on its mass, if it's extremely massive, it might go and become a black hole immediately. Otherwise, it might become a neutron star, might become a white dwarf. I don't have time to go into this too much. It's the conventional story that was sort of laid down in the 60s and the 70s, and to some extent the 80s. For cataclysmic variables, there are some different processes involved because mass transfer dominates the life of a cataclysmic variable. Here are the main processes. We start with a binary, just a run-of-the-mill binary, but with an orbital period of about 1 year. One of these stars is more massive than the other, of course, and that star will become a red giant first. There's the one. Becomes a red giant first. And it gets very close to this other star, and it basically envelops the other star. If the orbital is 50 years, it won't. But if it's about a year, and there's plenty of them like that, it envelops the other star. And you get this thing called a common envelope binary. And that's a big field of research now. It's a messy field of research. The common envelope binary phase only lasts a short period of time because there are tremendous frictional losses as this thing here, which is a star, okay, is orbiting within the atmosphere of another star, of a red giant. So there's tremendous frictional losses, so the binary period shrinks down to some small dimensions, and in a pretty short period of time, you get that. Only about 20,000 years. Very, very short period of time. So the number of stars that we expect to see like this is quite small, because it's such a transient phase. And also, it's a little ill-defined what properties they would have, because you can't see inside where all the churning is going on, of course. Okay, so I've been studying these stars for a long time, and I'm very interested in the oldest of these stars, and that's the thing I'm going to sort of conclude about talking about here. This is a little diagram for now all cataclysmics. After the previous thing is over, the previous slide is over with, a star might start out with an orbital period of maybe 12 hours or something like that. The secondary star is rotating rapidly because the tidal lock in one of these stars is very, very strong. Secondary stars are forced to rotate rapidly, about 130 kilometers a second. Now, the sun rotates at 2 kilometers a second. And your random G stars and K stars in the field rotate 2, 3, 5. Why do they rotate so slowly? They're formed around 400 kilometers a second. It's because at high speed, these late-type stars, at high rotation speed, these late-type stars eject extremely powerful stellar winds. And just as the ice skater slows down when she gets rid of the angular momentum associated with her spin, otherwise she would never come out of that inner spin. She throws out her arms, she slows down. Likewise, the star does. And so angular momentum is drained from the binary. And because the tidal lock remains strong, and so the star is forced to actually spin fast, even though it's lost its angular momentum. How does it get the extra angular momentum? Has to take it from the orbital supply. It's the only other large supply there is. So it takes it from the orbital supply. So in that way, stars get closer, closer, closer together pretty fast. Enough to drive accretion rates of 10 to the minus 8 or 10 to the minus 9 solar masses per year. So that will exhaust the secondary in about 10 to the 8 years or 10 to the 9 years, fairly fast. By the time you get down to the very short orbital periods, 1.3, 2 hours or so, now the time scales are much longer, and so this is the domain I've become very interested in lately. I must admit, I've been a lousy CBA honcho in recent years because I've just gotten a little too fascinated by this category here to publish my papers star by star. Kind of wanted to sum it all up in one grand scenario or so, but I promise I'm going to get better. I'm going to publish the papers star by star, and I'll at least look better to the world there. So this is a graph here of, I promised you before that you could measure the mass of the secondary by the precession rate. We have lots of precession rates. We've got about 150 of them now. We have a few other masses that we get from things like spectroscopy and things like that. And so I figured a very good quantity to measure that signifies age for a CV is the mass of the secondary. Now, some of them were born small, so it won't always work. But basically all the ones that were born big get annihilated with time. So statistically, measuring the mass, if you look at the properties of the CVs of lowest mass, you get the oldest ones. So if you do that, that's what this plot is here, where this is actually mass ratio. It turns out you actually get mass ratio instead of mass. Not too important because most of these white dwarfs are about 1 solar mass, so it doesn't matter too much. You can see there the mass ratio is very low, 0.1. If the white dwarf is 1 solar mass, that means this is 0.1. So 0.08 is the traditional end of the main sequence. There's the traditional end of the main sequence right there. So everything above here you would call a star. And everything below that line, like that, you would call, well, there's no name for it yet or something. I suppose you could call it a brown dwarf, but it didn't form. It's sort of a cannibalized star. It doesn't really have a name yet, and maybe it doesn't even deserve a name. It used to be a star, and it's just in a fix. It's in a jam because it's got this white dwarf stealing matter from it and cannot stop itself there. This graph here shows, so this is one of the, well, this is sort of the major prediction of this theory. The idea, the strong stellar wind from the secondary allegedly disappears for very, very low mass stars. It disappears for several reasons, one of which is the star doesn't have enough luminosity to support it. You really can't drive a strong stellar wind unless the star has a certain luminosity. Stars at 0.08 solar masses basically have no luminosity, no nuclear luminosity. And so the only other inevitable source of angular momentum loss is gravitational radiation. This is gravitational radiation, not the gravitational lens. Gravitational radiation is another, of course, major prediction of Einstein's theory of gravity, which is sort of confirmed. The binary pulsar back in the late 70s basically confirmed it, although people are building detectors all around the world to enter this golden era of gravitational wave astronomy, which might happen, it might not. Who knows if that would be true. Anyway, the big prediction here of this theory is that it goes around like a boomerang, and that's the theory, this line here. If these stars are all kind of fairly normal stars and fairly normal cannibalized stars being driven by angular momentum loss from gravitational waves, roughly speaking, the points follow it. By the way, these are all hydrogen-rich stars over here, hence the Hindenburg here. And had I plotted, there's about half a dozen helium stars as well, and they live over there, and I haven't shown them here, but there are some pure helium CVs as well. Anyway, that's one of my, I always get happy when I look at that plot, so just put it up there. Just wanted to remark that astrophysics can really be done on any budget. This should probably be called the economics of stellar astrophysics. And if you look at, for example, for among the compact star, types of compact stars, you find out the biggies are the neutron stars and the white dwarfs, and of course orbits, because they're the important ones are really found in binaries. And you look at these various ways of characterizing the star. Let's look at for example, the oscillation frequencies that they show. Most famous neutron star is the Crab. The Crab is rotating about with a frequency of about 30 hertz. The white dwarfs are rotating with a speed of about, with a frequency of about 0.03 hertz or so. Some of them a bit slower. 0.03 is somewhat normal there. And the orbit, of course, is much slower than that. It's about 0.003. If you look at the energies scale about the same, 30, 30, 0.03, 0.01. The energy in keV per nucleon, whoops, misspelled there, about a factor, notice you get about a factor of 1,000 everywhere in here. Here's a factor of about 1,900. Here's a factor of about something like the same. Here's a factor of 1,000 over here. The luminosity over here, whoops, ergs per second. The luminosity scale by a factor of about 1,000. The dynamical time scales scale by not too far from a factor of 1,000. And the money scales by a factor of 1,000. You want to study rotating neutron stars? It'll cost you about 100 million or so. Probably need an X-ray telescope to do that. If you have one, you can have a great hobby with the 10 to the 8 dollars invested there. These white dwarfs here, if you want to study them with high signal to noise and be, a player on the world stage there, cost you about 100,000, like something like a 24-inch telescope, 30-inch telescope. Be very, very well situated for that. On the other hand, these orbital effects that we study with, Medes and Celestrons, basically. And it costs around $1,000 or so. And if you look at these things, generally speaking, about 30 cents per microhertz gets you into the game. So it just confirms the old adage that the main difference between men and boys is the price of their toys. Thank you.
We have time for questions. John?
What's the typical relative mass of
The relative mass? The accretion disk would be about 10 to the minus 9 solar masses. Yeah, it seems to be pretty uniform, too. The high m dot ones receive it at a high rate and dump it at a high rate. The low m dot ones hangs around longer. They're on the border. They have optically thin, optically thick portions. Yeah.
Here you go.
Yeah. We have Brian Marsden's joke here? Well, we have to point it out, too.
By B.G. Pumpkin on October 31st, 1977.
Oh, we have another Halloween. Which is it? B.G. The Exploding Planet? Okay, yeah. So I got to read this because you guys can't read it. Tom Van Flandern, some of you know him, did not survive the explosion of the planet and is now expected back from the outskirts of the solar system in 5 million years, I think. Yeah, and is that a joke too? I don't know.
Oh, yeah.
Oh, the whole thing's a joke.
Occultation by the Earth.
Sunset? It says sunset? Of Mars.
There's Antinova Lyra, E. Lowell Bowl Observatory.
Jim Elliott's communication, is he a particularly obscure communicator? Is that the idea?
He's the royal ringer.
Discovered the rings of Uranus.
That prompted it, because it's 1977.
He issued an anagram.
Oh, just like Galileo. Devious fellow.
Any other questions?
You're familiar with Plan B and the assimilation of a small orbiting star inside of an
AGB star?
Yeah, giant red star. Basically going on to form a ring nebula.
Form what?
A ring nebula. A ring nebula, as opposed to a planetary.
Oh, I'm not really, no. I know there's a few with planetaries, but I'm not familiar with that one. No.